Thank you. It's a pleasure to be here giving this talk. This is my first time visiting China. I'm enjoying very much. So I want to talk about a result which is in the area of Ramsey theory. And more specifically, what we now call arithmetic Ramsey theory. So in Ramsey theory, the goal is to find patterns in a priori chaotic situations. So Ramsey's theorem states that if you have a large enough complete graph and you partition or you color the edges with, say, 3 colors, no matter how you do, no matter how hard you try, there will always be 7 vertices that are all connected with edges of the same color. So that's the kind of results Ramsey theory is interested in. In arithmetic Ramsey theory, we care about results that have an arithmetic flavor. So the structure, the patterns we want to find, they come from the operations of addition and multiplication in the natural numbers. So as a first example, the theorem due to Schur over 100 years ago. He showed that for any number of colors, there's some large n such that if I color or I partition the set of the first n numbers into R colors. Okay, so these are the numbers I'm going to color with the first color, the numbers I'm going to color with the second color, and so on. So any way we do this, you can do it randomly. You can ask your child to color the numbers, or you can ask the devil to choose the worst possible combination. No matter what you do, can people read back here? Maybe I'll. Can you read here? Yes, okay. So no matter how you do this, there's always some color and some x and y, such that x, y, and the sum are all in the same color. Okay. So another example, another famous theorem in this area, just to give the flavor, it's due to van der Waerden. He was actually answering a conjecture which ultimately came from Schur. And he showed that if we do the same thing, so I should say, so for any R, in this case for any K as well, there is some N, such that if we color the first N natural numbers with R colors, then there is some color and some X and Y, such that the arithmetic progression x plus y, x plus 2y, x plus ky is entirely contained in the color Ci. So both of these theorems, they promise us that I can always choose a large enough n. And in fact, the proofs of those theorems, the original proofs, they give some bounds on what the n is. And there is a lot of work on trying to find the best bounds we can place on n. So there is some n, but what is it? But I'm actually not interested in that question, in the sense that my tools cannot say anything about how large n is. So I can only say, well, these theorems have been proved before, but the kind of theorems that I can prove say things like this. So if you tell me how many colors there are, I know that there exists some n, but I won't be able to tell you even an estimate for what n is. There exists some. And so in this regime, where we do not care about bounds, these theorems are equivalent to infinite versions, where we color not the numbers from 1 to n, but we actually just color all the natural numbers. And this seems a weaker result because I need to color more numbers, but it's actually equivalent by something called the compactness principle. So for instance, let me reformulate now these two theorems. Again, these will be equivalent statements, but they will look easier to formulate. So I can erase this thing here, and I can replace this thing here with just natural numbers. And same thing over here, so I don't care about that. And I just call up all of the natural numbers, and so I didn't lose anything. The statements are equivalent. It's not obvious that they are equivalent, but they are. And so I prefer to formulate things in this way. Okay, so there's a famous strengthening of van der Waerden's theorem, proved by Semeredi, that was conjectured by Erdős Turan. So just to put it on the board, Semeredi theorem. So this was proved in 1975, and there's a long, beautiful history both before and after 1975. But I will skip the history. I'll just say what the theorem says. And it says that I don't need to color the natural numbers if I want to find arithmetic progressions. I just need to take a set A that is large enough in the following sense. So if the upper density of A, which I will define in the usual way as just, it's the proportion of the first n numbers, n here, the proportion of the first n numbers that are inside A, and then I take the limit as n goes to infinity. The limit may not exist, so I take a lim sup. And as soon as the lim sup here is positive, which is a weak condition in a sense, then A contains arbitrarily long arithmetic progression. So let me just do it symbolically. For every k, there exists x and y, such that we have an arithmetic progression inside A. So Semeredi's theorem strengthens van der Waerden's theorem because anytime the natural numbers are partitioned into R pieces, one of those pieces must have density 1 over R, at least. So certainly positive. Okay, and the next result I want to tell you is just to make this point that arithmetic Ramsey theory has been studied for many years. There are many results, and there are some very strong results, and this is one of them. So this is an extension of Semeredi's theorem due to Bergelsen and Leibman, and it was proved in 96. And they showed following. So first I need to give myself some polynomials. P1, P2, Pk, polynomials with integer coefficients. And I do need to assume that they have no constant terms. So Pi of 0 is equal to 0 for all I. Okay? So any polynomials with no constant terms. So then, for any, well, if A has positive upper density, there exists x and y such that, okay, maybe because I don't want to, someone will ask about negative numbers. So let's say A has, oh no, it really doesn't matter. Sorry, let me stick to what I wrote. Okay, there exists x and y such that x plus P1 of y, maybe, so x plus P1 of y, x plus P2 of y, and so on, all these numbers will be contained in my set A. Okay. So any polynomial progression, which is the name we give to these objects, can be found inside this set A. So just to explain why this generalizes Semeredi's theorem, if Pi of y just I times y, we recover precisely an arithmetic progression. I'm just erasing the theorem I didn't want to erase. due to Schur, but maybe people still remember. I'll just write here the important part. Schur's theorem was about those patterns, two numbers and their sum. And so there's a similar pattern we could ask here, which is what about two numbers and their product? So do we have a similar type of result? I really shouldn't have erased it. Let's look at van der Waerden's theorem. So the question is, if I partition the natural numbers into finitely many pieces, we're back into the coloring regime, can I always find a pattern like this in one of the pieces? And so at first sight, this looks more complicated than that one because we're using multiplication instead of addition. It's a bit more subtle. But actually, the fact that this is true is a corollary of Schur's theorem. And the reason is that if you give me a coloring of all the natural numbers, I will forget the color of every number except powers of 2, 2, 4, 8, 16. And this induces a new coloring of the natural numbers. And I just use Schur's theorem on that new coloring. And if you write this down, you'll see that you found a monochromatic pattern like this. So this is really a corollary of Schur's theorem that we can find this in the same color. And so then this leads to the following question. Or maybe I should call it a conjecture. So this was asked, I think, at several points by many people, but nowadays it's called the Heinemann conjecture. So I won't put the date. And it says the following: if I color the natural numbers with finitely many colors, some Ci contain a pattern of the form x, y, x plus y, and x times y. And so the surprising thing is that the conjecture is still open. We don't know the answer. We don't know if it's true or if it's false. So already in 96 we knew this. We know stronger results than this. And yet this question is still open. And so when I was learning this subject some 15 years ago, there was, so it wasn't even known this, whether this statement was true or false if we exclude x and y from this configuration. So just these two numbers in the same column. And this was not known, and so this was the question that I was studying in my PhD, and the theorem that I want to talk about today is that now we do know the answer to that weaker question. So if, so to be clear, so this is my theorem, and I think it was published in 17. If the natural numbers are colored with finitely many colors, some color Ci contains the sum and the product of two numbers. And in fact, I can also promise x will be in the same color. But we don't know yet if y is in the same color. So I hope the statement is clear. Let me tell you a bit about the history of this conjecture and this theorem. So Heinemann and Graham, as early as the 70s, in 79. So I'll just say like this. So in 79, and this was due to Graham and Heinemann. This was I believe this was independent work. So they checked the case of two colors. So if I just use two colors here instead of R, then they use the computer search And already in 79, computers could show that there is always a monochromatic pattern like this. But they only find one solution, or perhaps finitely many, because they were using a computer. So we didn't even know if any two coloring of the natural numbers would have infinitely many solutions, which is perhaps the right question to ask. But it was some indication that maybe the conjecture is true. And then nothing really happened until 2010. And in 2010, people started looking at analogs of this conjecture, not in N, but in finite fields. Okay. And so the first result, which is due to Shkredov, said that in a sufficiently large finite field, we have, okay, I'll be a bit vague on what I write. So I'll verbally say what the result is. So if you tell me how many colors you want to use, I'll give you a value that any finite field larger than that value, with a sufficiently large, depending on the number of colors, will have a monochromatic pattern like this anytime you color it with that number of colors. Okay. Is the statement clear? So in fact, Shkredov proved the density version of this result, but I don't want to go into that. So this was for, yeah, he didn't actually deal with arbitrary finite fields. He just dealt with Z mod P. And then in 2012, Stilarhuelo, I'm not sure I put too many L's. So yeah, so then he dealt with any finite field. But still the same configurations, x plus y, x times y. We didn't know about y, and that was finally settled in 2016. So there's some intermediate work here go into. So Green and Sanders, in 2016, they did x, y, x plus y, and x times y in Z mod PZ. And so around this time, so this is work about finite fields. But you can also ask the question in infinite fields. I should maybe say, so we're ultimately interested in the natural numbers, but in the natural numbers you cannot divide. And because multiplication is involved here, it's convenient to be able to divide, which is why people started looking at fields, finite and infinite. So in infinite fields, around 2016, so myself and Bergelson, we also did the patterns x, x plus y, x times y. So in infinite fields. Could you repeat? No, yeah, so no non-trivial things. Yeah, not 0, not 1, and not 2. Yeah, so. No, yeah, so you tell me how many colors you want to use, and then if the field is large enough, depending on the number of colors. This one. Yeah, but it's the same, yeah, I didn't write everything, but it's the same thing. So if you tell me how many colors you want to use, yeah, and here, okay, if you want the characteristic 2 fields, you may need to be a bit more careful in the exact statement, but okay, let's say characteristic 5 and above. Yeah, this is just Z mod P. I'm actually not sure what he did. but let's say characteristic sufficiently large. Eventually. Yeah, in fact, fields maybe larger doesn't make sense, but yeah, you can find enough solutions. So all these results actually show not just one solution, but positive proportion of all potential solutions. So we have non-trivial solutions, which is any way you define trivial, there will be non-trivial solutions. Okay, so yeah, so I think this is all the history. This is all that happened before my theorem there. And then since then, there's been a lot of really interesting developments. So I get the dates right. So it was only published this year, but it's been up the archive for a while. So a result of Bowen shows that so I'll be a bit more precise. So if n is colored with just two colors, so there exist infinitely many x and y, such that all four x, y, x plus y, and x times y are monochromatic. Okay. And then later, but paper that was published in 2024, so Bowen and Sabok, I should say Bowen was a PhD student, Sabok was his advisor, and so together they then were able to show the full conjecture in the infinite fields. Okay, so let me just say x, y, x plus y, x times y, any infinite field. And then by compactness principle, this implies the same is true for any finite field, again with the finite field of sufficiently large characteristic. Okay, so in fields we know everything, and I should mention as well. So even later than this, Allwise has extended this result to handle even bigger configurations. So maybe I won't tell you exactly what they are, but yeah. So this is still a conjecture, but there are much stronger conjectures out there. This is just the first case that we cannot handle. So this is the door we need to get through to then unlock many other things we expect to be partition regular. But so maybe let me not speculate on what those are. But in infinite fields, we already know something beyond this result. Okay, so I think maybe this is all the background. No, it's not. So there is a new result. It just came out this month by my colleague, Florian Richter. So 5 plus. And he found essentially a density proof of my theorem. Now, we need to be careful what that means. I didn't say it, but not every set with positive density contains this configuration. The set of odd numbers has density 1/2, and you will have trouble finding these patterns in there. But upper density, the one we've been using is just a shift invariant notion of density. So there are more abstract ways to define upper densities, plural, and some of them are not translation invariant, they are dilation invariant. And it turns out, this is what Richter noticed, for this kind of problem, dilation invariant is the more important notion. And so he built a dilation variant. So I won't explain too much into that. Density. So let's put notations such that if D of A is positive, then A contains x plus y, x times y. I'm not 100% sure if x is also in there, so let's just say x plus y, x times y. So the reason he and many other people were interested in a density version of this result is because usually in this kind of Ramsey theory, if you have a density version, you can get stronger coloring version. So really he wanted to prove the conjecture, but unfortunately it seems the methods don't quite work yet. So just really to say this area has seen a lot of developments and it's still being developed as we speak. So this is all we know, and now for the rest of the talk, I want to explain the proof of this theorem. Okay, so the way, I didn't say anything in any of these results about how the proofs work, but maybe I will now mention about these results. So this is when I started working in this project with Bergelsen. And we used methods from ergodic theory and dynamical systems to address these problems. And here it was very important that we were working in infinite fields. Well, just say very quickly, the reason that's helpful is that in infinite fields, we have the group of all affine transformations. So the group generated by translations and dilations is what we call a solvable group. So it's an amenable group. And so we can do ergodic theory in that group, and that was very important here. For the natural numbers, so we don't have a group. First of all, we have a semi-group generated by translations and dilations, and this semi-group is not amenable. So we cannot do ergodic theory in this group, which is why our proof didn't apply here. So what my idea was to essentially stretch the method of ergodic theory in such a way that it applies here. And I was successful, so I could do that. Once I wrote that down, I realized I had stretched ergodic theory so far that there was barely any ergodic theory left. And I could now write the proof without any dynamics whatsoever. And so I did that, and it turns out this theorem, the proof has less than 1 page in the paper. So when I was preparing this talk, I was considering what I want to do now. Do I want to tell you the proof, that is 1 page, or do I want to explain the proof? And I always tell my students, if you're giving a talk, explain the ideas of the proof, don't give the full proof. But now I will not take my own advice. I will present the proof, and then if I have time, I will explain the ideas, because that would take longer than presenting the proof. So there's some preliminaries I need. Okay, preliminaries. So facts that I will use. Fact number 1, if I have a set with positive density, and A is finitely colored, some, so I'll just write it in symbols. So there is some I, such that this density is still positive. So if I have a set of positive density, I break it into finitely many pieces. One of those pieces still has positive density. No argument there, I hope. Property 2, if I have a set with positive density and a natural number, the set n times A, which I always mean the dilations. So I multiply every element of my set by A, that's n times A, has positive density as well. So again, the density is exactly density of A divided by n. But I just care that it's positive. And the third property I need is essentially Semeredi's theorem that I formulated earlier. It's an averaging version of Semeredi's theorem. So if density of A is positive, then there exists some n such that A minus n minus 2n A minus kn is non-empty and in fact has positive density. And I should say for every k there exists an n. So for every k exists an n such that so you can look at the screens if you cannot see the front of the board. So this set here is just a set of A's for which the arithmetic progression A plus n, A plus kn is inside of my set A. Okay. So Semeredi's theorem, as I formulated it earlier, tells me that this set is non-empty. There is some arithmetic progression inside A, but you can run an averaging argument, if you know what that means, to conclude that there's actually a positive density set of such A's. So that's all I'm using here. So any question about the background? Maybe let me write a corollary of this, which is what I will actually use. I think it will make our life easier in a moment. So so let's say y1, yk, n, and A has positive density, then there exists n such that density A minus y1 times n, just dot A minus yk times n has positive density. So why is this true? Because I can take a very long progression, A minus n, 2n, 3n, 4n, all the way up to yk times n. And that entire intersection has positive density by Semeredi's theorem. And then what I'm doing, I'm just keeping some of those. So this set is larger than the one down there, for the larger k. Okay, so I will just use these facts 1, 2, and 4 to prove the theorem. So yeah, I already said my mindset when approaching these problems is through ergodic theory and dynamical system. So all the sets are sets of natural numbers, all the operations are in the natural numbers, but in a sense, in my mind, I'm really working in a dynamical system. And which is why I keep applying operations to sets. So I don't like to write elements directly. I like to write sets that intersect with their own translates. So I hope this is not too confusing, but it helps to present this proof. So, okay, and so if I want to prove the theorem that CI contains, let's forget X. X will be there for free at the end of the proof. We don't worry about it. But let's say I just want that pattern inside my set C. So X plus Y, X times Y inside the set C is the same as saying that that X is in C minus Y intersection C divided by Y. Okay, so if X is in this set, well, I didn't maybe define these things, but you can guess. So if X is in this set, it means X plus Y is in C. And if X in here, it means X times Y is in C. And so what I really want, I want to find a Y for which this is non-empty. And so for this to be non-empty, that's equivalent to saying when I multiply everyone by y, that this intersection is non-empty. And so in the mindset of dynamical systems and ergodic theory, I'm applying this operation, or rather this sequence of operations to my set C. So for each n, I apply this operation, I subtract y, multiply by y, and I want for some y to have recurrence. I want this image of C under this operation to intersect C again. So, okay, so this is just very, very vaguely what the idea of the proof will be. So let's start the proof now. So n is colored by the color C1 through CR. And now one of these colors must have positive density. I will just reorder the colors so that C1 has positive density. Okay, it will simplify a bit the writing. So say C1 has positive density. And so now I will start by using item 4. So then there exists some y1 such that C1 will come back after time y1, and the intersection will have positive density. Right? So far, so good. So I have here C minus y. So what I want to do now, I want to multiply this by y and hope that I intersect C again. So I will give names to these sets. This will be convenient as we go on. So let's call that D1. And I want to look at y1 times D1. Okay. I want to multiply this by y. Question? Okay, and now two things can happen. First thing that can happen, this set has non-empty intersection with the color C1. Let's look at that case first. So that means exactly that we write here. Okay, D1 is contained here. So if D1 times y intersects C1, it means that this intersection is non-empty. So I think if I write it in symbols only makes it more confusing. So let me say it again. So if this is non-empty, it means that, yeah, so this means that y times C1 minus y, my y's change a bit, intersects C1 is non-empty. And if you agreed with me up here, this means we are done. That was case 1. So case 2, if that doesn't happen, once, y1 times d1 is contained in the other colors, C2, C3, Ci. So I lose one color. And now I will use my property, well, I think I'm using property 2 and property 1 together. So property 2 tells me this set has positive density. So by property 1, I can choose a new color now whose intersection has positive density. To simplify the notation, I'll just assume that color is going to be C2. So without lots of generality, the density of Y1, D1 intersection C2 is positive. And so I'll give a name to this set. I'll call this B2. And now I will do the same thing again with an extra step. So I have a set with positive density. I will use property 4. I'll use the Moreira's theorem to find a new number, y2, such that, so let me, give it a name. So D2 is going to be some set has positive density. So this is what I did earlier. So what's D2? B2, B2 minus Y2, same thing as before. But now I will need an extra intersection. And this is where the magic happens, and I just have to believe me, this works. So we use here y1 squared times y2. So ultimately, why is this here? This is the derivative of the affine map yc minus y. This is not clear at all what I mean by derivative, and that's what would take me longer to explain than just write down the proof. So there's a reason to write this here, but we can check in a moment that this was the right thing to put here. So let's finish the proof here. Okay, so now a few things can happen. I want to multiply that set d2 by y2 again. So case one, if y2 d2 has non-empty intersection with the color c2, then I'm happy. This implies that y2 c2 minus y2 has non-empty intersection with c2. So I'm in this situation with 1. That case was easy. Now, I also want to rule out the case that y2 d2 has non-empty intersection with c1. If I can put a check mark here, then it turns out that this set is colored with only the colors 3 up to R. So I already dropped 2 colors, and then maybe you can believe me that you can keep dropping colors one by one. But so why is this case okay? So let's see. So let x tilde be in this intersection. y2, b2, and c2. Okay. So now we need to, unfortunately, we need to look through. So every element in D2, is in B2, and every element in B2 is a multiple of y1. Okay. So every element of D2 is a multiple of y1, and x tilde is in y2 times B2. So I can divide x tilde by y1 times y2. This is a natural number. And in fact, if we track down what happened, this natural number is in, I think all I care about it is that it's in C1. C1. Okay, and let y be y1 times y2. So y is not in C1, it doesn't matter. But x times y is x tilde, which is in C1. One moment. y1 C1. Okay, I miss, this is C1. Okay, so then x times y, this is at x tilde, this is in C1. Okay, we have half of what we want. Now we need x plus y. Okay, so what's happening to x plus y? So this is a bit difficult to analyze directly, so let's multiply this by y again. This is what I want to do. Okay, let's see what happens. I wrote this here, but maybe. Yeah. Okay, so let's multiply it not by y, just by y1. Okay, let's see what happens. Yeah, so y1 times x, so let's do some auxiliary calculations here. Y1 times x is in D1, in D2 rather. So it's this point here. And because it's in D2, I can add to it y1 squared plus y2, and it will still be in B2. So y1 plus y1 squared y2 is in B2. And now if we're lucky, this will come out. So B2 is in Y1 D1. And yeah, and this is in Y1 C1. Okay. So yeah, I don't know why I started writing there. So that's what I have here. So I'll rewrite it again. So y1x plus y, which was y1 times y2. When I multiply it with y1, we get this y1 squared y2, which now maybe you already recognize from this term here. And so this element here, y1 times x, is in D2 because y1 times x is the same as x tilde divided by y2. Okay, so there's too many variables to keep track of, but you can trust me, maybe, that, so this will be in B2. Okay. And then B2, if you keep track of everything, is in y1 times C1. So when I divide y1 on both sides, we get what we wanted. X plus y is in C1. And so as I promised, for free we got that x was also in C1. X times y, x plus y are all in C1. So this case is fine. And so we move to the case where I remove two colors. So okay, I'll maybe write it just a bit more. Okay, so otherwise, so y2, b2. So if it does not intersect C2, it does not intersect C1. It's contained in C3, C4, Ci. Okay, and so I can now find, or maybe I reorder the remaining colors again, so that the density of this set intersection C3 is positive. Okay, there's always one color for which the density is positive, because D2 has positive density, the dilate has positive density, so I need to be able to find a color for which intersection has positive density. Okay, and so now essentially we iterate the result. So let me do this in general, perhaps. So we have a situation where we have y n dn will intersect some color plus 1 in positive density. So then we use the Semerelli theorem to find y, let's do y n minus 1 d n minus 1 cn. Okay, so then we can find n, y n such that, oh, I didn't give a name. Okay, so this is what we call b n. And so we do bn minus yn. We do bn minus yn times yn minus 1 square. And we also need bn minus yn. And here we do yn minus 1 square, yn minus 2 square. And so we keep doing these intersections. So the last one is bn minus yn, and then yn minus 1 square, yn minus 2 square, y1 square. So this is how we use, in the general step, Semerelli's theorem. So, yeah, so then if this intersection which again I forgot to give it a name, so this would be dn. Yeah, and then if dn times yn intersection some ci, if this is non-empty, then I can always find x tilde in here, ci, and x will be just x tilde divided by all the y's, so yn minus 1, yn minus, no, yi. And y is going to be that product. And so from the construction, you can then see x plus y, x times y, and x are all in the color Ci. Okay, so we iterate, and that's the end of the proof. Yeah, so this is the end of my talk. Thank you.